In this question, the Hamiltonian of a system of n non-interacting spin-half particles is given here, where Siz, which is the spin component in an external magnetic field of the ith particle is given here. So, at a temperature T such that the given value is equal to T 2. So the e raised to this exponent is equal to 2 at this temperature T. The specific heat per particle is what? We're asked to calculate the specific heat capacity per particle. So first let's calculate the partition function. So we are given the Hamiltonian. So the Hamiltonian is nothing but and so half spin particles they have Siz, we have components plus and minus. Okay, so plus and minus 1. Now the partition function so we know the partition function is of the form generally we have the partition function e minus beta h, right? So this is the summation. So this is what I would write. So this is what I would write here. So e beta times the Hamiltonian. And there is another summation here which is on the I. So another summation on I. So this is so there are two summations. So I must note that. So this summation is over S, the number of so S1, S1, S2, going up to Sn. And this summation is over I. So S1. So now this can be written as to the power of n, because so there are in the power it is going up to n terms. So I'm breaking that power and writing it as a whole power of n. Okay, so that is what I'm doing. So now notice now S, what is S? It is plus and minus 1. So this can now be written this way. So if I have space here it will be good. Otherwise I have to go to the next page. So here this component Si to the power j is nothing but plus or minus 1. So I'll have to split this and write it as e to the power beta not p into 1 plus power of beta nu naught b minus 1. So this is nothing but your, so to the power n. So here I've just substituted for the value of si, I've just substituted plus or minus 1. So from there I get this term. So this is nothing but your hyperbolic function. So your cos h hyperbolic function. So it is, this is nothing but 2 times your cos h hyperbolic time, and the argument is b beta nu naught b and the power of n. So this is our partition function. Okay, so this is our partition function. Now we can find the, we have to find the specific heat capacity. So to find the specific heat capacity, I have to find the internal energy. The internal energy is nothing but minus partial derivative of, with respect to beta, of the partition function, ln of the partition function. So this, when evaluated, it gives us the internal energy. So here you have the partition function, so substitute it, and when you evaluate it, we get the internal energy. So this is nothing but minus n mu naught b tan h beta. Okay, so this is your internal energy. Now the specific heat capacity can now be found from the internal energy. So the specific heat capacity is nothing but du. So now we are evaluating the specific heat. So du by dt evaluated at a, so where evaluated where b is a constant. So when we do that, what we get is n times secant h square. So this I can simplify and write as now notice we want the specific heat capacity per particle, so I will divide it by n. So what I get is mu naught b. So now what I'm going to do is, we are given that we are make another substitution here. So this is nothing but kb So notice in the question we are given that this term is equal to 2. Okay, so that is e to the power of mu naught B by KB T is equal to 2. Therefore, mu naught B by KB T will be equal to ln of 2. Okay, natural log. So ln of 2. So therefore, this substitution is what I'm going to make now. So this is, so I have KB ln of 2 the whole square multiplied by 1 by, so cos h hyperbolic I'll substitute in terms of exponentials. So we have e to the power of beta whole square. So this simplifies to kb ln of 2 the whole square so the 2 I'm squaring it and taking it upstairs, and then this term denominator I am simplifying it to writing it in this fashion. You can check that this is the same as this. So beta I will substitute and write it in terms of, so beta is nothing but kb 1 by kbt, right? So so again beta I'm writing as 1 by kbt. So we know what is e to the power of mu naught b by kbt at temperature T. We just checked it in the question. It is given as 2. So this equation also now simplifies to kb ln of 2 the whole square into 4 divided by 4 plus 1 divided by 2 the whole square. So this is your answer. So the right option here in this question is given by the option D. So this is nothing but, you can check that this is nothing but 16 by 25 kb ln of 2 the ln of 2 the whole square. So this is your answer.